Second, resonance structure. So perfect segue into resonance. Resonance structures occur when we have several different possible arrangements of our electrons on the same skeleton. Generally, that means arrangements of multiple bonds and lone pairs. So if we go back to our example here, right, when we did this resonance, that, by the way, is a resonance arrow, right? So these are resonance structures of each other. The central atom arrangement, the single bond skeleton, is the same, but what we've done is we've moved lone pairs and changed multiple bonds and things like that, right? So the only thing that's moving here is lone pairs and multiple bonds. So just really quickly to review, we're going to do some more stuff, a lot more stuff with resonance this semester. So you can have more than 2 resonance structures, right? And none of the individual resonance structures completely describes the actual molecule. The real molecule is kind of a mixture of these, and I've shown you in the past some examples, and we're going to see examples of this in the future. So if that doesn't make sense now, we'll see this, okay? They are, however, not in equilibrium. So we draw the resonance arrow. That is not an equilibrium arrow. It's not like it's this structure changing back to that. What it's really saying is that each of these kind of partially depicts the overall properties of the molecule, but the molecule itself is just a mixture of these. Okay. The underlying skeleton doesn't change. What that means is if we took away all the multiple bonds and all of the lone pairs, what we would have left would just be atoms and single bonds. Those structures have to be identical for every resonance structure. If we're moving a hydrogen, if we're moving something, it's not a resonance anymore. It's a constitutional isomer. Okay. And then, and this was, somebody was asking about stability. The actual molecule is more stable than any of the individual resonance structures usually. Okay. Resonance adds stability. It's advantageous to have. So we're going to see that. Now, this then goes to your question, would those two be the same? Well, we can rank resonance structures that aren't like just some, kind of fundamentally identical. If they have a difference in them, we can rank them in terms of which one is more stable. And what we would see is the more stable ones contribute a larger percentage to the mixture, the hybrid structure. Okay. And so here's the order that we look at. And I'm sorry, it ran over the page, but structures with the most bonds tend to be the most stable. It's a big effect. Octet rule followers tend to be more stable, but you can see in that one, the hydrogen sulfate with the +2 sulfur and the 3 minuses was the octet rule follower, but actually the expanded octet would be more stable because it has more bonds, right? So there's like a priority order, okay? And then fewer number of formal charges tends to be more stable. And then this one is a little more subtle. We'll talk about it again, but basically when you have a positive formal charge on low electronegativity atoms and negative formal charge on high electronegativity atoms, that tends to be more stable. The opposite generally would be really unstable, but there are some exceptions to that. So we'll talk about that. I'm sorry I'm going fast. A lot of this is review, and I am going to post this video so you can rewatch it and ask questions. Feel free to stop me if I'm going too fast for stuff. We're going to use a method called pushing electrons to identify resonance structures from, a situation where we're just given a molecule structure. Okay. And when we push electrons for resonance structures, those movements are really imaginary. They're just showing how we could kind of figure out the other resonance structures, because really there's only one structure, there's no electron movement in it. But when in the resonance structures, we're showing them moving between them, okay? So, and to do this, we're going to use something called the curved arrow notation, all right? And the curved arrow notation looks something like this. Let me show you an example with resonance structures, and then maybe one with a reaction. sorry. So this is actually a structure that we're going to be making in a later chapter this semester, okay? It's a structure where we have a C double bond O carbon, and then directly next to it on what we call an alpha carbon, there is a negative charge. It turns out that this structure is possible because of resonance. And the resonance works like this. This pair of electrons pushes toward that adjacent pi bond. So it's pushing in between these two atoms. Now, I can make another bond here, but the problem is then carbon would have 5 bonds. So what we have to do is push a pair of electrons from the pi bond out onto the oxygen. So then what we're going to do is we're going to just draw a structure that's the result of moving these electrons. So if I take this pair of electrons and move it here in between these two atoms, I get a double bond there, right? I already had a pair of electrons. When I lay a second pair on top of it, it's an extra line. The other thing is that, do you notice this pair of electrons that was over the carbon is now gone because it's between the two atoms. When I take this pair of electrons and move it out, that, yes, it is allylic. Essentially, it is allylic. It's allylic to the C double bond O pi bond. Yes. Right? So we push this out. So what happens is now I have only a single bond because I took away a pair of electrons. And now I have 3 lone pairs on the oxygen, and I'm just going to fill this in. You can calculate that out. That would put a negative formal charge there. So we push electrons. Now the key is to note that when I pushed electrons, I started on the pair of electrons. I showed their destination, right? The arrow points to the destination. And that's really important when we do acid-base chemistry. I'm going to just show you a really quick example of this. We're going to talk about acid-base chemistry in our next section really quickly. So this is acetic acid. This is ammonia. It's a base. Ammonia can grab that hydrogen right there and make a bond to it. So what it does is it takes its pair of electrons and it basically takes that's like a stick and it basically plugs it into the hydrogen. Now the hydrogen can only have one bond. So when we make a bond on one side, we let go of the bond on the other. Okay, so now there's no bond to hydrogen here. There's just the oxygen. It already had 2 lone pairs, but now we put a third one on, and that's going to have a minus charge. And then over here, what's going to happen is there's now going to be a bond instead of that lone pair, hydrogen there, and that'll have a positive charge. And the point here is that what some people want to do that's incorrect so this is grabbing. Right? The base is reaching out. I don't know if you can see me, and it's grabbing that hydrogen plus. Some people want to do this. And I totally get why. They're showing this hydrogen moves to there. Right? That is incorrect. This is throwing. right? This is saying the acid throws the hydrogen and the base catches it, right? That's not how this works. The way it works is the base grabs the hydrogen. So the point is that if we look at this, we don't want to do this, right? Because that's showing an atom mood. Actually, on this one, I'll just show you really quickly. This is resonance stabilized. It's a similar thing. Is that what you're arguing? Or the negative goes to CP's dipole and particle? Are you talking about my first example or this example? Okay. So in the first one, we get the negative on C because actually what happened was it had a hydrogen and a base took away the hydrogen, and then the pair of electrons went onto carbon in theory, right? But it turns out that's spread throughout resonance. This one here, that one there is more stable of the two resonance structures because it's got the negative charge on oxygen, which is a much better place for it than being on carbon, right? Because oxygen is so electronegative. Again, we're going to talk about that in more detail, though. Send me a thing in Canvas if you have more questions. Okay.